To build a three-phase converter, you will need firstly 3 single-phase transformers with the same voltage ratings, secondly 3 high-power diodes rated for the required voltage and current, thirdly 3 electrolytic capacitors rated for the required voltage and capacitance, fourthly a 3-phase alternating current motor matched to the converter's output voltage and power rating, fifthly wire and connectors, and sixthly a multimeter. The steps are as follows. 1. Connect the transformers. Connect the primary windings of the transformers in parallel to the single-phase input voltage source. Connect the secondary windings in series, ensuring that the polarity is correct. 2. Add diodes and capacitors. Connect a diode across each secondary winding, with the anode connected to the positive terminal of the winding. Connect a capacitor in parallel with each diode to smooth the rectified output. 3. Test the converter. Using a multimeter, measure the direct current voltage between each phase terminal and neutral. It should be approximately 1.41 times the root mean square line-to-line voltage of the input source. 4. Connect the motor. Connect the motor terminals to the phase terminals of the converter, ensuring that the voltage and power ratings match. Start the motor and check its performance. 5. Fine-tune the capacitance. If the motor is not running smoothly, adjust the capacitance values of the capacitors until the motor operates optimally. Additional notes to consider. The voltage and current rating of the components must be sufficient for the desired converter output and motor power. Proper grounding and safety precautions should be followed when working with high-voltage circuits. The converter may generate harmonics which can interfere with other electrical equipment. The converter may require a cooling system if operating at high power levels. As an example, to build a 240 volts, 3-phase converter from a 120 volts single-phase source, use 3 120 volts over 48 volts transformers. Connect 3 1N4007 diodes. Use 3 1000 microfarads 250 volts capacitors. Connect a 3-phase motor rated for 240 volts and the appropriate power rating. Building a 3-phase converter requires electrical expertise and should be attempted only by qualified personnel. Improper construction or use can lead to electrical hazards or damage to equipment. The use of 3 single-phase transformers offers flexibility in voltage adaptation and isolation. Connecting the primary windings in parallel ensures they all receive the same input voltage, which is crucial for balanced operation. The series connection of the secondary windings allows for voltage stepping and the creation of a multi-phase output. Correct polarity is paramount to avoid short circuits or phase cancellations. Diodes are essential for converting alternating current voltage from the transformer secondaries into direct current voltage. Their placement across each secondary winding facilitates rectification, allowing current to flow in only one direction. The anode connected to the positive terminal ensures the desired current flow. Capacitors smooth out the rectified direct current voltage, reducing ripple and providing a more stable direct current supply. This smoothing is critical for the proper operation of the 3-phase alternating current motor. When testing the converter, the multimeter provides crucial feedback on the output voltage levels. Measuring the direct current voltage between each phase terminal and neutral allows for verification of the voltage output and balance between phases. The expected voltage is approximately 1.41 times the root mean square line-to-line voltage of the input source, reflecting the voltage transformation and rectification processes. Connecting the motor involves matching its voltage and power ratings to the converter's output. Proper matching ensures efficient operation and prevents damage to the motor or converter. Starting the motor and observing its performance is a critical step in validating the converter's functionality. Fine-tuning the capacitance is often necessary to optimize motor performance. Adjusting the capacitive values can improve the smoothness of operation, reduce vibrations, and enhance overall efficiency. The voltage and current ratings of components are fundamental to the converter's safe and effective operation. Insufficient ratings can lead to overheating, component failure, or even electrical hazards. Proper grounding is essential for safety, providing a path for fault currents and preventing electrical shocks. Safety precautions must always be followed when working with high voltage circuits to mitigate risks. The generation of harmonics is a common phenomenon in power electronic converters. These harmonics can interfere with other electrical equipment, causing malfunctions or reduced performance. Mitigation techniques such as filters may be necessary in sensitive applications. A cooling system may be required if the converter operates at high power levels. Heat dissipation is crucial for preventing overheating and ensuring long-term reliability. Fans, heat sinks, or liquid cooling systems can be employed depending on the power level and environmental conditions. Using 120 volts over 48 volts transformers in the example provides a specific voltage transformation ratio. This ratio determines the output voltage of the converter and must be carefully selected based on the desired application. The 1N4007 diodes are commonly used rectifiers suitable for many low to medium power applications. They offer a balance of voltage and current handling capabilities. The 1000 microfarads 250 volts capacitors provide sufficient capacitance for smoothing the rectified direct current voltage in the example. The voltage rating of 250 volts ensures they can withstand the maximum voltage levels in the circuit. Selecting a three-phase motor rated for 240 volts and the appropriate power rating ensures compatibility with the converter's output. The power rating should be chosen based on the intended load and application. Remember, building a three-phase converter requires a thorough understanding of electrical principles and safety practices. Only qualified personnel should undertake this task. Improper construction or use can lead to serious electrical hazards or damage to equipment. The three-phase converter described utilizes a combination of transformers, diodes, and capacitors to convert single-phase alternating current power into three-phase alternating current power. This conversion is essential for operating three-phase equipment in locations where only single-phase power is available. Firstly, the transformers are used to step up or step down the voltage levels as needed. Secondly, the diodes rectify the alternating current voltage into direct current voltage. Thirdly, the capacitors smooth the direct current voltage to create a stable power source. Fourthly, the configuration of these components generates a three-phase output. It is very important to understand the functionality of each component to design and build a safe and effective converter. Consider the following points. The transformer should have appropriate voltage and current ratings to handle the input and output power requirements. The diodes should be selected based on their forward current and reverse voltage ratings. The capacitors should have sufficient capacitance and voltage ratings to provide adequate smoothing. The wiring and connections should be properly sized and insulated to prevent overheating and electrical hazards. Proper grounding is essential to ensure safety and prevent electrical shock. The entire system should be housed in a suitable enclosure to protect it from environmental factors and prevent accidental contact. Regular maintenance and inspection are necessary to ensure continued safe and reliable operation. This DIY approach allows for customization and cost savings, but it also requires expertise and caution. Always prioritize safety and consult with qualified professionals if needed. Remember, electricity can be dangerous, so proceed with caution and follow all applicable safety regulations. The basic principle of this converter is to create three alternating current voltages that are 120 electrical degrees apart from each other. This phase shift is achieved through the use of the transformers and the arrangement of the diodes and capacitors. The transformers provide the necessary voltage transformation and isolation. The diodes rectify the alternating current voltage, and the capacitors store electrical energy and release it in a controlled manner to smooth the voltage waveform. The combination of these components results in three alternating current voltage waveforms that are phase shifted, creating a three-phase power supply. This three-phase power supply can then be used to operate three-phase motors and other equipment. Always use appropriately rated components. For example, do not use 16 volts capacitors on a 24 volts rail. The reverse recovery time of the diodes need to be considered. This is because the diodes will have to switch on and off very quickly. A standard rectifier diode like a 1N4001 is not suitable for high-frequency applications. The components should be mounted on a suitable chassis or circuit board. The wiring should be neat and organized. All connections should be secure and properly insulated. Consider adding fuses or circuit breakers to protect the converter from overcurrent conditions. Test the converter thoroughly before connecting it to any equipment. Use a multimeter to measure the voltage and current levels at various points in the circuit. Monitor the temperature of the components to ensure that they are not overheating. If any problems are detected, troubleshoot the circuit and make necessary repairs. Be sure to thoroughly label and document the converter. Include a schematic diagram, a parts list, and operating instructions. This will make it easier to maintain and troubleshoot the converter in the future. The design of a three-phase converter involves a balance between several factors, including the desired output voltage, the input voltage, the power rating, the efficiency, and the cost. These factors must be considered when selecting the components and designing the circuit layout. A higher output voltage will require transformers with a higher turns ratio. A higher power rating will require components with higher current and voltage ratings. A higher efficiency will require components with lower losses. A lower cost will require more cost-effective components, but be mindful of not sacrificing quality. The selection of diodes and capacitors plays a crucial role in the performance of the converter. The diodes should be selected based on their forward voltage drop, reverse recovery time, and current rating. The capacitors should be selected based on their capacitance, voltage rating, equivalent series resistance, and ripple current rating. It is essential to consider the thermal characteristics of the components when designing the converter. The components should be mounted in a way that allows for adequate heat dissipation. Heat sinks may be necessary for high-power components. The enclosure should also provide adequate ventilation to prevent overheating. It's also important to consider the electromagnetic compatibility, or EMC, of the converter. The converter may generate electromagnetic interference that can affect other electronic devices. Shielding and filtering may be necessary to reduce electromagnetic interference emissions. Designing and building a three-phase converter requires a thorough understanding of electrical engineering principles, including circuit analysis, power electronics, and electromagnetic compatibility. A three-phase converter is a versatile device that can be used in a wide range of applications. Understanding the design and construction of a three-phase converter can be a valuable asset for electrical engineers and technicians. Some of the steps provided are not necessarily written in the order of execution. Please use your own judgment on how to build the project.